Okay, welcome to the Principle of Organic Chemistry, Chapter 6, Functional Groups. Okay, so we have moved from Chapter 1, 2, 3, 4, 5. So now we are entering Chapter 6. For this week, we're going to talk mainly about the alcohols, amines, and phenols. Next week, we're going to talk about aldehyde, ketones, and carboxylic acid. Okay, so let's look at the first one, alcohol, phenol, and amines. So, before I go further about the about explaining about the different functional groups, it's very important for you to understand why you must learn about functional groups. Okay, because a lot of molecules, okay, especially food-related molecules, is quite complex in structure, and usually the molecule for food-related molecule, you will realize or found it could have one or more of these functional groups on this molecule, okay, the food-related molecules. And these functional groups actually give a certain properties to this molecule. Okay, so similar molecules with these functional groups, they have similar properties. So we sort of like, when we look at the a different part of the molecules, okay, even though we are not familiar with, but as soon as we identify these functional groups, we say that it has certain properties. Okay, maybe you can say that it's soluble in water. Okay, small molecules, maybe you say that it has a very low melting point, or maybe a very low boiling point, so possible that it's going to be aromatic and so forth. Okay, and you realize also see some certain things. You say that because it got this functional group, possible to have certain reactions. Okay, so for this chapter, okay, chapter 6, now you're going to get to know, okay, learning about different functional groups and how these different functional groups actually, what kind of properties they have, okay, and what kind of reactions they can actually reacted with other type of functional groups, maybe to generate a certain certain type of molecules at the end, okay, which give you a certain another type of properties. Okay, let's look at the first one, okay, which is the alcohol, phenol, and amine for this week. So it's very important for you to know how to name and draw the structural formula for these functional groups. Okay, alcohol, phenols, and amines. Able to classify the alcohol and amine as primary, secondary, or tertiary on the basis of their structural formula. It's very important for you to able to differentiate between these categories, okay, primary, secondary, and tertiary, because it got to do with their reactivity. Okay, I'm going to explain that later on, yeah, when we reach the chapter, reach the part. Discuss how hydrogen bonding influence the physical properties of alcohol and amines. Very important. Physical properties, you need to uh, gauge about their physical properties so that you know how to manipulate these molecules, okay, especially in the cooking or processing conditions. Yeah, recognize uses for specific alcohol, phenols, and amines. Okay, so you can know what these molecules are for. Okay, let's look at the first one, alcohol. Alright, so alcohol, the functional groups is basically hydroxyl. Okay, so the hydroxyl group is the functional group of alcohol. So you will see that the hydroxyl group is characterized by the O and H. Okay, O and H, and this is what we call hydroxyl. Okay, O and H. Okay, so this one is O and H. The oxygen atom forms a sigma bond to the carbons and hydrogen atoms and two unshared paired electrons. Okay, so what it means by two unshared paired electrons? Unshared paired electrons is this. Okay, so one pair of electrons, one pair of electrons. These pair of electrons are not shared to either atoms. It's not shared to hydrogen, it's not shared to carbons here. Okay, so it's unpaired. And what happened, right, is these two unpaired electrons, you push this hydrogen downwards. Okay, so this one will be over here, and this one will be pushed down. That's why you can see that there's actually a band over to this structure. Okay, there will be a band to this structure, and the two unsure paired electron will be here. Yeah. Okay, so because of this, there's a there's a not symmetrical structure. Okay, as you learn from previously, because of this, okay, then there is a because it's also a polar bond. If you see this, calculate the differences in electronegativity, you know that this one is actually a polar covalent bonds, and with this asymmetry of this structure, you know that this one is a polar molecule. Okay, so this one will be a polar molecule. Over here will be a delta positive, here will be a delta negative. How you assign this delta negative, delta positive, okay, means slightly negative, slightly positive at this end. How how you assign this is through their electronegativity. Yeah, so we have already done this part. Okay, we have already gone through this part. If you are still not familiar with, look at chapter 2. Okay, look at chapter 2. So, okay, so this one is polar molecules. Yeah. So how to give a name to alcohol? Alcohol are named the same way as alkanes. Alkene, what we have learned before, exactly the same. Okay, same thing. You need to look for the longer chain. Okay, and then this longer chain must contain the hydroxyl group. When you name it at the end of the molecule, instead of E, you put OL. Okay, so normally it's like ethane. Okay, instead of ethane, now is ethanol. Okay, low with the OL at the back there. Yeah. And then use a number to show the location of the OH group. Yeah, name and number substituent and list them in alphabetical order. Okay, make sure of this. Yeah, alphabetical order. So, if you have ethyl, methyl. Okay, so you have a methyl, you have a ethyl. Okay, so which one should come first? Because this is E, this is M, so this one should come first. Okay, name that first, then only you name the metal. Okay, so for number 2, ethyl, 3, metal, and so forth. Alright. So this one you can see from here, this one is not C, yeah, so the C is here. Okay, so this one is ethanol. So here got three of the carbon. Okay, it's prop. Okay, propan 1 because it's located at carbon number 1. Okay, 1, 2, 3. This one we got 3 carbon, 1. Okay, CH3, CH, and CH. So 1, 2, and 3 carbon here. 1, 2, 3 as well is fine. Okay, so this one OH is located at carbon number 2, so propan 2O. And this one is 1, 2, 3, 4, CH3, CH2, CH2, CH2. So 4 carbon butyl, and then carbon at carbon number OH at carbon number 1, so it's butan 1O. Sometimes, right, you do need to have the 1 as well. Okay, so you can call it as a butanol. Okay, it's fine. Flexible with that, yeah. So how about giving names to compound with 2 hydroxyl groups? So in this case, if you have more than 1 hydroxyl groups, okay, you can name by giving a location. Okay, for example here is okay, carbon number 1 and carbon number 2. Okay, and you add one more because of 2 hydroxyl group, you put it diol. Okay, di 2. Okay, diol. In this case, you have 3, 1, 2 triol. Okay, so propan triol. By the way, this one is the glycerol. Yeah, glycerol, one of the very common ingredient in the food industry. Yeah, okay, and glycerol is also one of the group okay, the primary groups for the oil and fats. Yeah, so glycerol will attach to 3 fatty acid to form, okay, oil, okay, or what we call triglyceride. Later we'll touch that, yeah. Okay, for alcohol, right, you can actually differentiate into primary, secondary, and tertiary. Okay, for you to categorize into primary, secondary, what you need to do, right, is you need to look at the carbon directly attached to the OH group. Okay, so you need to look at this, yeah. If there's there's nothing to attach to it, or possible this one is if you want to extend, you can extend to C. Okay, there's no alkyl group attached to it. Alright, so it's a C. As long as that, this is a primary alcohol. Okay, but when you got two, you only got one, yeah. If you got two, so you can, this one can be longer chain, no problem. Okay, this one can be longer chain, no problem. As long as there's a two, then it's a secondary. If here got three, okay, so either is CH3 or here can be longer. Okay, C, okay, longer, no problem. As long as you got three, then it's called a tertiary. Okay, so why is it important for you to know about primary, secondary, and tertiary? This part, later on, you'll be utilize it for the aldehyde and ketones, okay, reactions in the ketones and aldehydes, yeah. For example, the primary alcohol will reacted in such a way that it will form the form a different type of groups. Yeah, later I will talk about that one. Yeah, I don't want to confuse you at the moment. Yeah, so primary, secondary, and tertiary. Okay, it has a different type of the reactivity, especially for the aldehyde and ketones. Later we will touch on that when we reach next week. Yeah, next week. Secondly is the reactivity also. You can see for here, so this one is more or less, even though it's long, but this OH group is at the end of the group. Okay, whereas this, you can see that there's a bulk phase surrounding the OH group, and this one is have a bulk phase surrounding the OH. So what it means, right, is that here there is sort of like a protective effect towards the OH. So making the reactions towards this OH group is difficult. Okay, this one is difficult, but not as difficult as this one because it's not got two groups. This one is the easiest because it can directly react to OH group. So in terms of reactivity, this one will be easiest, followed by this. This one is very difficult. Yeah, this one is very difficult because of the bulk. Okay, because it's a carbon with 3 hydrogens surrounding it, and this one is a vicinity of the OH group, so it's protecting the OH group against any reactions here. Okay, so I have mentioned about the polarity of alcohol, so you can actually calculate based on the electronegativity. So we check the covalent bond for this and realize that these two are polar covalent bonds. Okay, if you do not understand, go back to chapter 2 and revise it. So since these two are polar covalent bonds, so we can identify which one is slightly negative, slightly positive. How we know that is through the electronegativity, because the oxygen has a stronger electron, which that the electrons will slide to the oxygen. Okay, slightly go to the oxygen. Okay, so you can see 3.5. Carbon is only 2.5. Hydrogen is only 2.1. So the electron will pull towards the oxygen. So here will be slightly positive. Here will be slightly negative. Here will be slightly positive. Yeah, this is due to the polar covalent bonds. Okay, polar covalent bonds means that it's unequal sharing in electrons. Yeah, and because of the non-symmetry structure, okay, because of the non-symmetry, lone pair electron pushes this down, okay, and forming this structure, then this would be the alcohol are polar molecules. Okay, so I mentioned a few slides early on. Yeah, looking at the physical properties. Okay, physical property usually we talk about boiling point, melting point, solubility in waters, and you can see that the boiling points is quite relatively higher if you compare to the alkanes of similar molecular weights here. Okay, so if you compare these two, one is ethanol, one is alcohol, one is the non-polar non-polar alkanes, you can see that there's a big difference in terms of the boiling point. It's very similar molecular weights, but you can see the methanol has a higher boiling point compared to this. Okay, when you comes to this, right, think about it. When you talk about boiling point, you're talking about intermolecular force. Molecule, how they interact, intermolecular force. So when you talk about alkanes, how they interact, dispersion force, very weak, okay, easy to separate. So you don't even need a lot of heat, okay, it's already separated and is in the gaseous state already. Whereas for the methanol, because it's through hydrogen bonding, okay, so is stronger in terms of intermolecular force. That's why the boiling point is at 65 degrees Celsius, which means that you need to heat the methanol. If it's in room temperature, you heat up to 65 degrees Celsius, only you can disrupt this interaction and make them independent of each other to change from a liquid phase to a gaseous phase. Yeah. So because this is a non-polar covalent bond, okay, non-polar molecule, that's why it's insoluble in water, because you remember water is a polar molecule. Okay, polar molecule interact with polar molecule. For methanol, it's a polar molecule, so it can interact with polar molecule. Yeah. But as you see from here, when the alkane light chain, you can see here, this part here, okay, is getting longer and longer. What happened? You can see that the boiling point is still high, still getting higher, okay, because of the dispersion force as well as the hydrogen bonding, okay, is strong. But you can see that there's a decrease in the solubility because this part, okay, this part doesn't like water, only this part like water. That's why the solubility decreases. As long as you got two of these OH group, look at it, back to infinite insolubility. Alright, so the food molecule, if you look at it, right, same thing. You look at the overall structure, okay, identify what are the functional groups they have. You more or less you can gauge their physical properties. Then you can know that, oh, this one is soluble, this one not soluble, and so forth. Okay, so that you know how to manipulate them in your formulations. Okay. So alcohol have a higher polarity than alkane or similar because alcohol are polar and can associate by hydrogen bonding. Okay, especially this one, the type of hydrogen bonding is between O and H is stronger compared to N and H. Okay, and so forth. Yeah, this is a stronger hydrogen bonding. Yeah. So why is boiling point solubility in water higher than alkanes? You can see this is stronger. Okay, because of the interactions. Okay, because of the interaction, and here you see compared with alkanes, the boiling point is a lot higher. Yeah. How about the acidity and basicity of alcohol? If you're looking at the pKa, okay, or the acid ionization constants, you can see that the alcohol, you can see here, alcohol with the functional groups, the pKa is very similar, very close to water. Okay, so the alcohol is neutral, more or less neutral, not acidic nor basic. Okay, so I don't want to hear anyone say that alcohol is acidic or basic. Yeah, no, yeah. Alcohol is more or less very similar like water. The pH quite neutral. Yeah. You can see that the alcohol can be converted into a lot of other type of the groups, okay, other functional groups. The one that I really highlight just now is the change alcohol to aldehyde and ketones. Okay, just a bit of a review, okay, which I wanted to keep until next chapter. Like primary alcohol primary alcohol can reacted to aldehyde, okay, and secondary alcohol will be reacted to ketones. Okay, secondary alcohol not to here, but here. Okay, the reason is the location of the OH group. Very important. Okay. So ethanol can be prepared. Ethanol is one of the biofuel. Okay, that is gaining more and more popular for the past 10 to 15 years. Okay, because it's renewable energy. Why is it renewable? Because you can actually create from fermentation of sugar. Can be from sugar canes, or grains and so forth. Yeah. So nowadays, the engines also, they're looking at producing engines that burn from ethanol, because burning ethanol actually is quite clean. It directly, without creating too much of the greenhouse gases. Yeah. So alcohol can be produced industrially by vapor phase hydration of ethene. Okay. So other than the fermentation process, go through these reactions where the hydration of the alkane. Okay. So you can create a ethanol. Okay. So we have learned previously. Yeah. What happened, right, is that later you see from the carbonyl groups also, okay, where you can sugar, okay, or what we call glucose, can be reduced to a alcohol group. Okay, so this one is aldehyde. Okay, later you will learn this as well. This one is the aldehyde group. So when it reduce, okay, not oxidized, it can be reduced to a alcohol group. Okay, the alcohol, this one is what we call the artificial sweeteners. Okay, or what we call alternative sweeteners. Okay, this one is what we call sugar alcohols or polyols. That the calories are significantly reduced. Okay, once you convert these glucose to sorbitol, the calorie largely reduced. So the calorie is much lower, and also the conversion from here to here. Okay, although it got affect the sweetness level a bit, but it's okay. Okay, because a lot of people, why they want to use these sugar alcohol, or what we call polyol, to actually polyol. Why they want to use the polyol or sugar alcohol is to reduce the calorie. Because if you want to have all this in the mouth, okay, why you want to be in your mouth as well, you do not want to have extra glucose in there that promote the bacteria from growing, because bacteria utilizes glucose to create energy for them to grow. Okay, whereas this polyol or sugar alcohol does not actually metabolized by the bacteria. So what happens is that your mouth still can remain fresh. Okay, that's why a lot of them, they use it to make it chewing gum, okay, eclipse and so forth. Yeah. The alcohol can also be converted to ester. This one is through the reactions between the ethanol or alcohol and carboxylic acid. Carboxylic acid is a weak acid. Yeah. The reaction between these two, ester and flavor ester. Okay. In this case, once ethanol and butanoic acid reacted in the presence of acid catalyst and heat, it creates what we call the ethyl butanoate, which has the pineapple fragrance. Okay, so we will learn that later on. Yeah, the conversion of ester. You will learn this as well in the aromatic and flavors. Yeah, the subject. This one is considered as a synthetic flavor. Yeah, synthetic flavor, because you use the chemicals as well as the chemical reactions. This one is considered as a synthetic, so you cannot claim as natural. Later on in the subject, I will teach you some other method as well to create the flavor molecule, but yet you can categorize or label it as natural, which is currently the in thing now, yeah. People are very into this natural ingredient sort of thing, yeah, because they think it's healthier for them. Okay, that one I will keep it to later on, yeah. So this one is the summary of the reaction. Alcohol can be oxidized, okay, and then if it's primary, it can be oxidized to aldehyde. It can, if it's secondary, it can be oxidized to ketone, but it cannot oxidize to tertiary, yeah, because this one, as I tell you, tertiary alcohol is quite not reactive because of the bulk of these three groups that protecting the OH group. This one, the aldehyde can be further oxidized to form hydroxy acid. If it's the other way around, you can see from here, yeah, if it's the arrow is the other way around, it's called the what we call the reduction, yeah. You can reduce this from carboxylic acid to aldehyde, reduce to a primary alcohol, okay. And this one, it can be reduced to secondary alcohol. So the reaction is two ways, depending on what you use. We are using the oxidizing agent or a reducing agent. Okay, so that's it for the alcohol. Next, okay, next we will talk about phenols. Okay, phenols. Let's look at the phenols. So got one more, yeah, after phenols, we still got amines, okay. So what are phenols? Phenols are hydroxyl group attached directly to an aromatic ring. Again, this one is very, looks very similar to alcohol, but it's not because the OH group directly attached to it. As soon as if there's one more C over here attached, then that one is alcohol already. It's not phenol. Phenol is directly attached to this. Aromatic ring is the 6 carbon ring, 1, 2, 3, 4, 5, 6, with alternating double, single, double, single, double, single bond, yeah? So all the termination we have mentioned just now. So how to give name to phenols? Okay, don't worry about the phenols exams, not going to come out because not really related to the food, not too much, okay, but some molecules they do have the phenols, yeah. So phenols, okay, so this is 3-methyl-phenol. Usually when you give the numbering, this is 1, 2, and 3, okay. You come from the OH group, yeah, 1, 2, 3, so is located at carbon number 3, yeah. If the other way around is too far, yeah. So here, so 3-methyl-phenol. This one is 1, 2, if 1, 2 here, no problem, okay, 1, 2, benzene diol, okay, in this case, instead of calling it as an aromatic, you call it as a benzene ring. So 1, 4, 1, 2, 3, 4, 1, 4 benzene diol, okay, with 2, yeah, 2 of the hydroxy group. Okay, if you're looking at alcohol and phenol, what's the difference? Okay, there are a lot of difference here. Because of the aromatic ring, you can see that the acidity is different as well. Phenol is much more acidic compared to the ethanol. Okay, you can see much lower. Okay, you might be wondering why is it more acidic compared to alcohol? It's because of this ring structure. It tends to pull the electrons away, making the H, the OH here, the H to dissociate into hydrogen ion. Okay. The more it pulls, what happens is that the more it pulls, by having one group over here, it pulls stronger, come out more easily. You see, the acid strength increases. This one is even stronger. What happened? It pulls the electron stronger. This one easier to come out. That's why the acid strength gain. Okay. So you can see in tutorial some of the examples here, very interesting here, how you identify that. Okay, in the tutorial you see as well, there's one that trick you by having one more C over here, and that one is actually alcohol. So the pH is more than neutral, yeah. So don't get tricked by it, yeah. So no, unlike alcohol, ester cannot be prepared by treatment of phenol. Phenol is very unreactive, okay, because of the aromatic ring as well as the the OH group, yeah, directly attached to the ring, okay, not very reactive, yeah. A lot of reactions is not really there, yeah. So where can you find the phenol, like these phenolphthaleins, okay, which is one of the indicator for titrations, okay. Under certain of the pH, you can change from once you hydrate to a certain pH, you will change from a clear solution to a pink solution, okay. The reason why is it we change color at certain of the pH, okay, is because of this ring. Every time remember, yeah, with this ring, it can absorb the light, okay. But in this case, it required to align to a certain degree where it absorb the lights, okay. So at first maybe it's like that, okay. So at first maybe it's like that. As the pH change, it turn, and then it change to pink color. In this, maybe it will attach, it will absorb the pink color, absorb colors other than pink color. That's why you can see pink color, yeah. Okay. So it's the rearrangement, the pH is affect the rearrangement of these rings, which affects the color, yeah, that you observe. Other than that, you also can find this ring in the vanillin. Okay, vanillin is the primary flavor for vanilla flavors. Okay. Okay. Other than that, you can see thymol, thymes. Okay, is one of the very aromatic the ingredients. Okay, thymes, and the active ingredient is thymols. Okay, you can see there's a ring as well. Then you can see the last one examples is bisphenol A, BPA. BPA is actually not food ingredients here. It's actually a plastic. Nowadays you can see that your bottles are all listed there. BPA free, BPA free. Why is it BPA free? Because BPA has been banned in 2012 because it can mix the body's own hormone and lead to negative health effects here. Okay. This BPA is initially is actually banned for using it for manufacturing baby bottles, but now I think most of the bottles are now BPA free. Yeah? Okay, the last functional groups I want to talk about this week is the amines. Okay, what are amines? Amines are derived from ammonia, NH3. Okay. So for amines, you also can classify into primary, secondary, and tertiary structures. Okay, but this is different because instead of for the alcohol is you need to base on the carbon directly attached to the OH group, but this one is not carbon. Instead, you look at the nitrogen. Okay. So you concentrate on the nitrogen. If you got one group attached to it, it's primary, no longer, no problem, it's still primary. When you got two groups attached to it, it's secondary. Got three groups, it's called tertiary. Yeah? So again, alcohol groups, you look at the carbon directly attached to the OH group, whereas this one, instead of the carbon, you look at the nitrogen. Okay, nitrogen. Same thing, the reactivity is less. Okay, and this is the best, yeah. Okay, same thing, this one, the group CH3 any groups is shielding the reaction, the nitrogen from reaction, yeah. Yeah, so this one is what I've just mentioned. So you can classify amines as well as aliphatic amines. Okay, when this one is in the alkane chain line. Okay, then you call it as aliphatic amines. If directly as you call it aromatic amines, and if the nitrogen is inside the ring, you call it as a heterocyclic amines. Yeah, this one is just a different terminology. That's it. Okay. Okay, looking at the physical properties, okay, so you can look at the bonds between N and H. Between N and H, right, you can see that it's actually a polar covalent bond. So because it's a polar covalent bonds, then you can assign a delta positive and delta negative based on their electronegativities. Yeah? And in this case, when the A minus and A minus interact with each other, it's actually a hydrogen bond. But this hydrogen bond is different from the other hydrogen bond. The other hydrogen bond is O and H, yeah, the alcohol, O and H. But this one is H. If you check this N and H, the difference in electronegativity is lesser compared to the O and H. What does it mean? Lesser difference in electronegativity. Okay? Lesser difference in electronegativity means that the interaction is weaker. The O and H has a greater difference in electronegativity. So the hydrogen bond is stronger. Alright? So you can see from here, you can compare between the OH and the A minus. You can see although the molecular weight is very, very similar, but you can see the bonding time very big difference. This is stronger than this. This is a lot higher than this one. Okay, although both of them they are hydrogen bond, but the N and H hydrogen bond is weaker compared to O and H. Okay. Okay, looking at the physical property solubility, because it's a non-polar covalent bonds, and also if you look at it, it's a polar molecule. Okay, if you look at it, it's actually a polar molecule. So in this case, right, it's soluble in water. Okay, very, very soluble in water. If you're looking at the acidity or basic, okay, for A minus, just like ammonia, ammonia is a base. Okay, ammonia is a base because it can accept the hydrogen ion. Yeah, because it can the proton or hydrogen ions. Okay, that's why it's basic. You can see all the A minus, they are very basic here because it can accept the hydrogen ion. By the way, all this ammonia, okay, very good cleaning agent. Yeah, as I say, higher pH is very good cleaning agents, okay, as mentioned in the Coloration 101. Where can you find A minus? A minus usually it is one of the byproduct from the breakdown of proteins, okay, or maybe an indications from fermentations. When you fermentation, the protein can break down and you form A minus. So sometimes people use the A minus to indicate how much it has been fermented, or you can use the indication concentration of A minus to see whether it has been on the shelf for a very long time. Okay. The natural chemical content of A minus also increases as food mature. Banana ripens. Okay, meat ages. All these they can an indicator of the microbial spoilage as well. Okay, with the increase of A minus, sometimes it can tell you these informations. Okay, so you can use it as one of the indicator to look at the how good is still your product, or maybe how much it has already fermented, how much it has been aged, the meat. Okay, use this as an indicator, the amount of concentration of A minus. Okay. Okay, so I will stop here. That's it for this week. Okay, so do remember to actually indicate if you have got question. Ask the questions in the palette. If you got no question, please indicate no question in the palette. Yeah. All right. So thank you very much. Okay.